AWS Lambda launched in 2014. The pitch was simple and intoxicating. Forget servers, forget provisioning. Write a function, deploy it, pay per invocation. The server is someone else's problem. 12 years later, serverless is mainstream, and somehow so is Kubernetes, which is the exact opposite philosophy. Kubernetes says, here's a full orchestration platform. Now learn about pods, deployments, services, ingress, namespaces, RBAC, CRDs, operators, Helm charts, and about 40 other things. Both are thriving, which tells you something. It tells you the original serverless promise didn't fully land. And now we're in a second wave, Serverless 2, edge functions, WebAssembly runtimes, and the cloud architecture debate is back with new stakes. I'm Alex. This is Bot Thoughts by Amtok Soft. Sam, you've watched this play out from the infrastructure side. What actually happened between Serverless 1 and where we are now?
The story of Serverless 1 is a story of a brilliant idea that hit real limitations at scale. The promise was compelling. Functions as a unit of deployment, automatic scaling from 0 to millions of invocations, and a billing model where you pay only for compute you consume. For event-driven workloads, webhooks, image processing pipelines, notification handlers, scheduled jobs, this worked beautifully. But when teams tried to build entire applications on Lambda or equivalent platforms, they ran into a set of problems that are now well documented. Cold starts were the first one everyone noticed. The first invocation of a function after a period of inactivity incurs significant latency, anywhere from a few hundred milliseconds to several seconds depending on the runtime and memory allocation, because the platform needs to spin up a new execution environment. For a user-facing API, that's a terrible experience. The second problem was state. Serverless functions are stateless by design, which means you need external services for everything: databases, caches, file storage, sessions. Your infrastructure cost and complexity didn't decrease, it just moved. Third, observability was hard. Distributed tracing across a system of hundreds of tiny functions, each with its own lifecycle, was genuinely difficult with the tooling that existed in 2014 through 2020. And fourth, local development was painful. You couldn't easily run Lambda locally in a way that faithfully reproduced the production environment. These weren't fatal flaws, but they were real enough that organizations running complex systems found Kubernetes, for all its ceremony, gave them more control and predictability.
So what changed for Serverless 2? Because I keep hearing that term, but I'm not always sure what specifically is different. Is it just marketing, or are there concrete technical improvements that address those problems?
There are three concrete things that changed, and they're all significant. First, cold starts are largely solved for mainstream runtimes. AWS Lambda introduced SnapStart for Java. It takes a snapshot of an initialized execution environment and restores from that snapshot rather than initializing cold. The latency went from multiple seconds to under 100 milliseconds. More broadly, the micro-VM technology that AWS uses internally, Firecracker, which they open-sourced, boots in about 125 milliseconds and uses around 5 megabytes of memory overhead per VM. That's the infrastructure underlying both Lambda and Fargate, and it's why isolation got dramatically better while cold start times came down. Second, the execution environment became more capable. Lambda functions can now run for up to 15 minutes, use up to 10 gigabytes of memory, and access ephemeral local storage of up to 10 gigabytes. That's not a toy compute environment anymore. Third, the developer experience improved significantly. The serverless framework, AWS SAM, and especially the AWS CDK gave developers better local emulation and infrastructure as code tooling that made the gap between local and production smaller. So Serverless 2 is less about a new paradigm and more about the original paradigm becoming genuinely reliable for a broader range of workloads.
There's another dimension to the serverless renaissance that I think is actually more interesting than Lambda improvements, which is edge functions. Running serverless compute at CDN PO PS geographically close to users. Cloudflare Workers, Versal edge functions, deno deploy. What's the significance of that shift?
Edge functions represent the most interesting development in the serverless space in the last 5 years. The premise is this. Instead of running your function in a single region, say a CEAST, you run it simultaneously at every point of presence in a CDN network. Cloudflare has over 300 PoPs. When a user in Tokyo makes a request, the function executes in Tokyo, not in Virginia. The latency is dramatically lower because the compute is physically close to the user. But here's the constraint that makes this engineering interesting. You cannot run a full node, JS or Python runtime at 300 locations simultaneously with acceptable startup times. The cold start problem is magnified at the edge because you need sub-millisecond startup everywhere, all the time. That constraint is precisely why WebAssembly became the runtime of choice for edge functions. Cloudflare Workers runs on the V8 JavaScript engine with a custom isolate model. Each function is a V8 isolate, not a full VM or container. Isolates share the V8 engine process but are completely sandboxed from each other. Startup time is under a millisecond. Memory overhead is kilobytes, not megabytes. You can run 5,000 of them simultaneously on a single machine. That's a completely different resource model than Lambda, and it's why edge functions can operate at genuinely global scale in a way that traditional serverless architectures cannot.
Okay, so WebAssembly comes up in the context of edge functions. But I want to dig into this because WebAssembly, as a server-side runtime, feels like a significant claim. Most people know Wasm from running C or Rust code in the browser. How does that translate to server-side, and why is it compelling enough that serious infrastructure companies are betting on it?
WebAssembly was designed with 3 properties that make it interesting beyond the browser. First, it's sandboxed by default. The Wasm spec defines a memory-safe, capability-based execution environment. Without explicit grants, a Wasm module cannot access the file system, network, or any system resources. This is structural isolation. You don't need a full VM or namespace-based containerization to get strong isolation between untrusted code. Second, it's near-native performance. Wasm compiles to a portable binary format that a Wasm runtime then JIT compiles or YOT compiles to native machine code. For compute-intensive workloads, image processing, video transcoding, compression, cryptography, Wasm runs at speeds within 10 to 20% of native compiled code. That's dramatically faster than interpreted languages like Python or JavaScript. Third, it's genuinely cross-platform. A Wasm binary compiled once runs on any platform with a Wasm runtime. x86, ARM, Linux, Windows, Edge nodes, browsers. The system interface is standardized through WASI, the WebAssembly system interface, which defines how Wasm modules interact with the host operating system in a portable, capability-restricted way. What you get from combining these 3 properties is a deployment artifact that is lighter than a container, faster to start than a VM, safer by default than either, and runnable anywhere. Fermi's Spin Framework and Cosmonic's platform are building production serverless platforms entirely on Wasm runtimes. Bytecode Alliance is standardizing the component model that will define how Wasm modules compose with each other. This isn't a browser technology that got repurposed. It's becoming a serious server-side runtime.
So if WebAssembly has all these advantages over containers, lighter, faster startup, better isolation by default, why aren't we all running Wasm instead of Docker? What's the catch?
The catch is ecosystem maturity, and it's a significant one. Docker and the OCI container ecosystem have 12 years of production tooling, community knowledge, and compatible software. Almost every programming language has first-class support for building containers. Every CI/CD platform, every cloud provider, every monitoring tool knows how to work with containers. The list of software available as container images is effectively infinite. WebAssembly as a server-side runtime is maybe 3 years into its production journey. Language support is uneven. Rust and C have excellent Wasm compilation targets. Go support is good, but has some caveats. Python support exists, but the runtime is larger and slower than you'd expect. Many languages don't have mature Wasm compilation targets at all. WASI is still evolving. WASI Preview 2 standardized in 2024 and brought component model support. but tooling is still catching up. The observability story, distributed tracing, metrics, structured logging, is less mature than for containers. And the operational knowledge in the industry for debugging a Wasm-based system in production is thin compared to the extensive documentation and community experience for Kubernetes workloads. So the honest answer is, for new Rust or Go-based stateless workloads, Wasm Serverless is genuinely compelling today. For migrating existing applications, you're looking at real porting work and operational risk. The trajectory is clear. Wasm will eat more of the serverless space over the next 5 years, but containers aren't going away.
Let me bring Kubernetes back into the picture, because I think the framing of serverless versus Kubernetes is a false binary in some ways. Kubernetes has its own serverless and event-driven story now. KEDA Knative, you've got auto-scaling to 0 on top of Kubernetes. So what is Kubernetes actually doing in this landscape?
You're right that it's not a binary, and the evolution of Kubernetes is actually one of the more interesting stories in infrastructure. Kubernetes started as a container orchestration platform. You manage pods, deployments, services, and the scheduler places your containers on nodes. That core hasn't changed. What has changed is the abstraction layer being built on top of it. KEDA, the Kubernetes event-driven autoscaler, lets you scale any workload, including to 0 replicas based on external events. Q-depth, Kafka topic lag, HTTP request rate, database query count. You get serverless-style auto-scaling behavior on top of your existing Kubernetes cluster. Knative takes this further, providing a higher-level programming model for deploying and managing serverless workloads on Kubernetes. Auto-scaling based on HTTP traffic, event-driven function invocation, a declarative eventing system. Google Cloud Run is the managed version of this pattern. It's native on GKE, presenting a serverless API surface while running on Kubernetes underneath. The practical significance is that you don't have to choose between serverless behavior and Kubernetes control. You can have event-driven, auto-scaling to 0 workloads sitting alongside stateful, long-running services in the same cluster, managed by the same operators, visible in the same observability stack. For organizations that have already made the Kubernetes investment, this is often the path of least resistance. Rather than adopting a separate serverless platform, they add KEDA and get serverless behavior where they need it.
There's a provocative question I want to ask directly. Is Kubernetes going to be a legacy technology in 5 years? I see people arguing that platform engineering is abstracting it away to the point where most developers never touch it. And eventually, the abstraction collapses and Kubernetes disappears from the developer stack entirely.
I don't think Kubernetes is going to disappear, but I do think it's going to become invisible to the majority of developers, and that's a meaningful distinction. The trajectory of platform engineering is to abstract the complexity of Kubernetes behind internal developer platforms. You don't need to understand pods and services and ingress controllers if your platform team has wrapped all of that behind a simple deploy command or a git push workflow. The developer writes code, pushes it, and the platform handles everything: container builds, deployment, scaling, certificates, service mesh configuration. From the developer's perspective, it looks like serverless. From the platform team's perspective, they're running Kubernetes and making all those decisions once on behalf of the entire organization. Kubernetes is becoming infrastructure, the way TCP/IP is infrastructure. It's there, it's essential, but most people building on top of it don't think about it directly. What will become visible is the next layer of abstraction, the internal developer platform itself, or managed platforms like Google Cloud Run, AWS App Runner, Render, Railway, which present simple deployment surfaces while running Kubernetes or equivalent orchestration underneath. The comparison I'd make is to the database. MySQL and PostgreSQL didn't die when Aurora and PlanetScale appeared. They became the substrate. Kubernetes is on that trajectory.
Okay, real practical question. I'm a developer or a small engineering team. I'm starting a new project. How do I actually think about this decision in 2026? What are the signals that push me towards serverless, edge functions, Wasm, or Kubernetes?
Here's the framework I use. Start with the access pattern question. Is this primarily event-driven or request response? If your workload is fundamentally about reacting to events, file uploads, queue messages, webhook calls, scheduled triggers, serverless is a natural fit. The scaling model aligns, the billing model aligns, and the operational overhead is low. If it's request response with continuous traffic and tight latency requirements, you need always warm compute, which means either containers or a serverless platform that keeps your functions warm. Second question, how stateful is your application? Truly stateless workloads, API gateways, transformers, validators are great candidates for serverless and edge functions. Stateful workloads with complex in-memory data structures, long-lived connections, or large local state are better suited for containers. Third, what's your team's operational capability? Kubernetes has a steep learning curve and significant operational overhead even with managed services. If your team doesn't have Kubernetes expertise, starting with a higher level abstraction, Cloud Run, Fargate, a PaaS is almost always the right call. You can always go lower if you need to. The opposite path, starting with raw Kubernetes and trying to climb up, is where teams sink months of engineering time. Fourth, are you building at the edge? If geographic latency matters, global user base, real-time interactions, personalization that must be fast everywhere, edge functions are genuinely compelling. Cloudflare Workers, Versal Edge, Deno Deploy. For most teams, the answer to the first decision is, use a managed container platform. Cloud Run on GCP, App Runner on AWS, or a PaaS like Render or Railway. You get container flexibility with a managed operational surface. Revisit the decision as your scale and requirements become clearer.
Let's talk about cost, because that's where serverless either shines or becomes a trap depending on your traffic pattern. What does the cost math actually look like?
The cost math is highly traffic pattern dependent, and getting it wrong is how teams end up with unexpected bills. Serverless billing is per invocation and per GB second of memory used. At low and spiky traffic, a few thousand invocations per day, bursty patterns, serverless is extremely cost-efficient. You pay only for what you use with no idle compute. AWS Lambda's free tier is 1 million invocations and 400,000 GB seconds per month, which is genuinely useful for small workloads. The economics flip as traffic becomes continuous and high volume. If your function is receiving thousands of requests per second, continuously, around the clock, you're paying for every invocation plus the memory consumption. At that point, a dedicated container instance running continuously is often cheaper per request, because you're amortizing the fixed cost of the compute over a high request volume rather than paying per invocation overhead. The crossover point varies by workload, but a rough heuristic is, serverless is typically cheaper up to around a few million requests per day, after which dedicated compute, containers or reserved instances, often wins on cost. There's a third scenario that's less obvious, serverless with external service dependencies. If every Lambda invocation opens a database connection, you can create connection pool exhaustion at scale, because Lambda's scaling is designed for stateless compute and databases have fixed connection limits. RDS proxy solves this for AWS, but it's an additional cost and operational layer. The cost conversation for serverless has to include the full stack, the function, the data layer, the observability, not just the compute line item.
Vendor lock-in is something I hear about a lot with serverless, less so with Kubernetes. Is that a real concern in practice, or is it overstated?
It's a real concern, but the scope of the lock-in is often misunderstood. The logic layer, your function code itself, is usually portable. A Lambda function written in Python or Node can be adapted to Cloud Functions or Azure Functions with relatively minor changes. The lock-in is primarily in the integration layer. The event sources, the triggers, the IAM configuration, the VPC networking, the observability setup. If your Lambda is triggered by SQS, reads from DynamoDB, and sends results to SNS, migrating to GCP means replacing all of those integrations with GCP equivalents, PubSub, Cloud Spanner, or Firestore, different IAM model. That migration is significant even if your core logic is portable. WebAssembly and the component model are explicitly designed to reduce this problem. A Wasm component with a WASI-compliant interface can, in theory, run on Fermion Spin, Cosmonic, Cloudflare Workers, or any other compliant Wasm runtime. The portability is at the binary level, not just the source level. That's a genuinely different portability guarantee than what you have with Lambda. Kubernetes reduces lock-in at the orchestration layer. The same Kubernetes manifests work on EKS, GKE, AKS, or a self-managed cluster. But you're still locked to the managed services attached to those clusters. No infrastructure strategy completely avoids vendor dependencies. The practical question is which dependencies carry the highest migration cost and whether the business value of a given cloud's managed services is worth that cost.
There's an angle I want to bring in that I think changes the calculus: AI workloads. Running inference at scale, running AI agents that make API calls, handling streaming responses. Does the serverless versus containers versus edge analysis change when AI is the workload?
AI workloads expose the fault lines in this debate very clearly. For inference serving, running a model and returning predictions, the requirements are often orthogonal to what serverless does well. Inference can be compute-intensive and latency-sensitive, which means you often want GPU access, consistent response times, and warm model loading. Cold starting a GPU instance that loads a multi-gigabyte model is exactly what you don't want in a serverless architecture. That's why NVIDIA's Triton Inference Server, VLLM for LLM serving, and managed inference platforms like Modal and Replicate use persistent, warm, container-based compute rather than function-as-a-service patterns. The one area where serverless does work well for AI is orchestration and pre-post processing. Your Lambda can receive a request, call a managed inference endpoint, process the response, and return results, all without holding a GPU instance idle. The GPU-hungry inference itself is a separate persistent service. For AI agents, which make sequences of API calls, potentially spanning dozens of tool uses, there's an emerging pattern of using durable workflows: temporal for complex, long-running agent orchestrations, AWS step functions for simpler sequential workflows. These are neither purely serverless nor containerized. They're a hybrid model where the workflow state persists durably, and individual steps can be serverless functions or containers depending on their resource requirements. The AI workload makes the multi-tier compute architecture more explicit, not less important.
Let me push you on where this is heading. If I told you to draw a picture of how cloud architecture looks in 2028, what does it look like? Is there a convergence happening, or does the fragmentation get worse?
I see convergence at the platform level and fragmentation at the infrastructure level, and that's actually a stable state. At the platform level, what most developers interact with, the experience is going to look increasingly like pushing code and describing what you want. How many replicas, how much memory, what events trigger it, what services it needs access to. The underlying implementation details, whether it's running on Kubernetes, a Wasm runtime, Firecracker VMs, or something else, become invisible. The platform layer makes those decisions based on the workload's requirements. At the infrastructure level, you'll see more specialization. Wasm runtimes optimized for edge and serverless. GPU-optimized instances for inference. High-memory, fast local storage instances for databases and stateful compute. RDMA-networked clusters for distributed training. The infra is getting more specialized, but it's abstracted away from most developers by the platform layer above it. The other trend I'd call out is sovereign and on-premises cloud. The regulatory and data sovereignty requirements for financial services, healthcare, and government are pushing significant compute back on premises or into regional clouds. Kubernetes is the dominant platform for private cloud, and that's not changing. So the 2028 picture is managed platforms and edge functions for most developer-facing applications, Kubernetes as the substrate for private cloud and complex enterprise deployments, Wasm becoming the runtime of choice for new serverless and edge use cases, and AI infrastructure as a distinct and rapidly growing category with its own requirements.
That's a clear picture. Let me pull together the key things to hold on to from this conversation.
Here are the 4 things I'd put on a whiteboard. First, Serverless 2 is real. Cold starts are largely solved for mainstream runtimes. Edge functions provide genuinely global serverless compute with sub-millisecond startup. The platform maturity gap between serverless and containers has closed significantly. Second, WebAssembly is a serious server-side runtime, not a browser curiosity. Lighter than containers, faster startup than VMs, sandboxed by default. The ecosystem is maturing. Rust and Go support are production-ready today. Wasm will take a meaningful share of the serverless and edge market over the next several years. Third, Kubernetes isn't dying, it's becoming invisible infrastructure. Platform engineering is abstracting it away from most developers. KEDA and Knative bring serverless behavior to Kubernetes clusters. Most developers in 5 years will interact with a platform layer, not Kubernetes directly. Fourth, use the right tool for the access pattern. Event-driven, bursty, stateless workloads fit serverless. Continuous, stateful, complex workloads fit containers. Edge functions for global latency requirements. AI inference as a distinct, specialized tier. And start with managed platforms, Cloud Run, App Runner, Render rather than raw Kubernetes, unless you have a specific operational need and the expertise to back it.
Where should people go to learn more about any of this? Serverless, Wasm, the platform engineering angle.
For the Wasm side specifically, the WebAssembly component model proposal on GitHub is the best technical reference for where the standard is heading. Fermian's documentation on Spin is an excellent practical introduction to building Wasm-based serverless applications. Lynn Clark's explanations of the component model are some of the clearest writing on the topic. For serverless architecture patterns, the AWS well-architected serverless lens is comprehensive and worth a full read even if you're not on AWS. Yan Kui's blog, The Burning Monk, has years of Lambda production experience condensed into practical, specific guidance. For the Kubernetes and platform engineering angle, the CNCF's Platform Engineering White Paper is the canonical reference on internal developer platforms. Luca Galante's work on platform engineering at Syntasso is very practical, and our blog has a post on Cloud 3, hybrid, multi-cloud, and sovereign architecture that covers how these pieces fit together at the organizational level. On YouTube, we have a video coming on Serverless 2, that'll be V030, which walks through the architecture decisions and trade-offs visually. Worth watching alongside this episode.
AWS Lambda is 12 years old. Kubernetes is 11. WebAssembly as a server-side runtime is maybe 3. The cloud architecture story is still being written, and the decisions being made right now, which platforms win, which runtimes become default, how AI workloads change the infrastructure calculus, are genuinely important for anyone building software. Sam, this was a great conversation. Lots to think about. That's Bot Thoughts by Amtalk Soft. I'm Alex. If this episode was useful, subscribe wherever you listen to podcasts. And if you want to support independent tech content, buymecoffee.com/AmticSoft. It genuinely helps. Back next week with another one. See you there.